Now we are discussing diagonalization, and this means that here we have a diagonal matrix. The diagonal matrix has only non-zero values on the diagonal, so it looks something like we have some value here, some other value here, and here there are only zeros, so there can be some value, let's call it B, there's some value A. So this is our diagonal matrix, and okay, if you have a bigger matrix, then it looks something like this, and we can go on like that. And if we think about it, if we have a matrix and eigenvectors, and here we have the inverse of this eigenvector, something interesting happens actually. These eigenvectors get just scaled by a transformation, and then we can put these scaled eigenvectors back into the eigenbases, and then something interesting happens. And here I have a quick walkthrough. So, first things first, we are transforming the eigenvectors of A with A. What happens is that they just get scaled. But per definition, they just get scaled by the eigenvalues, by the corresponding eigenvalues. And that's okay, but now we want to actually do this. We multiply them on the left side by P inverse, so what puts them back into the eigenvector bases, and then something interesting happens. Look at this graphic here. We know we have an eigenvector of this transformation, and then in this thing here, we have it just stretched by its eigenvalue. And what we do now is we want to transform, this is also another eigenvector here. And now what we do is we transform them back into the eigenvector basis to get this diagonal here on the right side. So what we have here is interesting, because if I want to express this vector in eigenvector basis, what do I basically say? Well, I say I have this vector here, lambda, so eigenvector 1 times, so I have an eigenvector here. And how often do I need to have this vector to express this one? 0 times, so I have 0 times this vector. How do I get those vectors? This vector I just get by saying, well, this vector I have 0 times, and this vector I have lambda 2, eigenvector 2 times. So these are just placeholders, just to visualize that I have taken lambda, so the eigenvalue 1 for v2 and 0 times v2 and these. This means just how we actually combine them. So we have to get this diagonal matrix with the corresponding eigenvalues on the diagonal. And this is super interesting because it allows us to decompose our matrix A into P, dP minus 1. And this is just rearranging the terms here. So, now something interesting happens. What if I want to take A to the power of 2? Well, this is the same as just multiplying this with itself. So, this times this. But what we see here is that this is just P inverse times P. And everything multiplied by its inverse is just its identity. That's the definition of an inverse. So we can just get rid of this thing here, because it's just an identity, you know, equals to identity. Doesn't change anything. And we can do this obviously as many times as we want, so we can just say A to the power of n equals P d to the power of n, P inverse. And how does the diagonal look like? Well, it just has the eigenvalues on it. So if you compute this and take it to the power of n, the only thing that changes is that these eigenvalues get taken to the power of n. So this is very fast to compute if we have to use this transformation multiple times. Then you have to use it 1,000 times or whatever. And if you do it like this, that's very easy. If you do it with A, that's very slow. And we're going through an example, and we already found in the last video the eigenvalues and the corresponding eigenvectors. So with this matrix, it was quite easy to find. And now we want to find this P, the D, and the P inverse. So D just has the eigenvalues on the diagonal. So this is really easy to find. Just plug those in, and we have the diagonal. Perfect. Check. Then we want to find P. P is also easy to find because we see P just contains the eigenvectors. We already know the eigenvectors, so we just plug in here V1, V2. This is 1, 0, 1, 1. Check. We have found it. So P inverse now is a little bit tricky to find, but as you should already know how to solve a linear system of equations, we know P times P inverse equals the identity. So we are searching for P inverse in this example. So what we are doing, we want to bring this to a form where it looks like we reduce this to the identity, have P inverse, then we have P inverse on both sides. So we just have to reduce this to the identity. So this thing here equals P that we already found here. And here we just have the identity. And now what we're doing is we're doing our row operations that do not change the linear dependency of the columns and reduce this to the identity. And then we have P inverse here. So let's just go over this, how this worked. So this already looks close to finished because we only have to get rid of this one here. So what we can do is we just subtract this row from this row. This row is unchanged, so this is the same. So we have 1 minus 0. Well, this is 1. 1 minus 1. This is 0. 1 minus 0 stays 1. 0 minus 1 is minus 1. So this is P inverse, and here it is. It's easy. That was quite easy to find. We have an easy example here. It gets a little bit more tricky for not so set up examples. And now let's check it if this is right. So we know P times P inverse per definition is the identity. And let's see if that works. So P inverse, it's just this matrix multiplication. So what we're doing now is think about matrix multiplication like dotting these. So we dot this with this. This is 1. We dot this with this. This is 0. 1, 0. We dot this with this. Well, this is 0. 1 minus 1 times minus 1 plus 1 times 1, 0. And we dot this, this with this. This is 0 times minus 1, 1 times 1, 1. So this is the identity. That's what we should get. Don't forget, this is the identity. This is P inverse. This is P. So this works fine. We could also reverse this. It would be the same thing. And now what we got is we have the decomposition. So we know our matrix A equals P D P inverse. And obviously, we can also take this to the power of n, and it is the same thing. And we can check if that's right, or if I was telling lies here. And we can do that easily by just using P here, D here, P minus 1. This is an easy way to set up matrix multiplications. So we are dotting this one. Okay, this is 1, 0, 2. And this is also 2. So we have this thing here. This is PD. You can write this down. This is PD. And then we just have to matrix multiply PD with P inverse. So this is 1. This is 1 as well. This is 0. And this thing here is also 2. So this thing here must equal A. What is A? This thing here. And we see it's the same thing, so this worked out just fine.